Professor? About the homework, 1E.
Yeah, I'm about to talk about it.
Yeah.
So listen, thanks for pointing it out to me. Some people have already. So a couple of things I want to talk about. First off, I just learned that you could not see these assignments, right? It looks like it's not fully graded, but it is actually fully graded. But what I did was I tried to do a trick on Gradescope so that I would lump a lot of yeah. So all of these here, I moved them to one problem so that I don't have to go through this entire set again and again and again, right? So everything is graded, but you don't have access to it. I'm sorry about that. Did anybody get an email about this homework that it's graded? Really? I even sent you an email about it, but through Gradescope, but clearly it didn't. But so I really apologize about that. I like the homework to be done at least a week before the exam, so at least graded. So I'm really sorry about that. The other thing is that I'm sorry about is this homework here. That's I don't know whether it's this one there. Yeah, so I won't try the trick again. It didn't work out well over here. So there's an error, a couple errors actually, in this homework assignment. So here, the first problem I think is the only one there's an issue with, right? Anyway, so we want to construct a Hamming code over here, and the strategy to do this is kind of the same as what you've done in the previous homework, right? You're given that this is irreducible over F5, so here's your finite field, and notice, this A is primitive, so here's a full listing of all the powers of A, and notice that as you take these powers, at some point you hit the number, you hit a number in F5, here in this case it's 3, and from here onwards, every power of A that appears over here gets scaled by a factor of 3. Right, so notice that here we have 3a squared. If you look at the first 3 entries, so it will be 3a squared, and then it will be 3 times 2a plus 3. That will be 3 times 2 is 1, 3 times 3 is 4. That will be a plus 4. So a plus 4 should be the next, and there it is. Follow? Right, so we have 3. So this whole block over here gets multiplied. This whole block over here gets multiplied by 3. Until I get to this point, until I reach number 4, and then the whole block gets multiplied by 4, and so on. So my point is that the scalar multiples start appearing after this point onwards, right? The whole block gets repeated. But anyway, that's not what I wanted to talk about. We construct a parity check matrix using the first 31 of these. I think it's the first 31, right? So where does the error begin? So the errors begin over here. So if you got up to D, you should be good, right? So the first error is that for part 2, right? So 1E part 2. I want you to explain why f of A, not cubed, but f of A to the 5th power is equal to 0, and f of A to the 25th power equals 0. Right, so this part of here, we already know that f of A is equal to 0, that's from the first part. So we see that f has at least 3 zeros, A to the 5th, A to the 25th power, right? Where else did I make a mistake? This 3 over here should be 5. Right? So in part 4, it's F5. Modulo x to the 31st. Do I have that right? Yeah. Yeah, so what I'm trying to show over here is prove that that Hamming code constructed in the first part is really a cyclic code. And the generator polynomial is the same polynomial that we use to construct the finite field. Right? So that's the goal over here. And in fact, any Hamming code is a cyclic code if you construct it correctly. If you order the rows of your pattern check matrix appropriately, you will get a cyclic code. Right. So the other thing is, well, I think there's nothing else. There's no error. No, I think it's been proofread at least twice, so it's good, right? There's no other errors. Yeah. So those two errors. I'll send an email out about that and fix it. Okay. So I want to continue. So we have very limited time now. We have this week, next week, and then your exam is on when?
It's on
The 18th.
On the 18th.
Monday.
So we have a whole week break after the last week of class. Is that it? Okay, that's good, right? Did any of you watch the video recording of the lecture last week? No? That is 1, 2 of you? 3? No? Okay. Right, so let me just repeat some of it. Let me just see if I can find this. Right, so I left, there's part of it that everything that I did last week was very, what do you say, algorithmic. I showed you a method to do something. And I informed you that I'll be proving that this week. So, so here is the proof of that. So let me just find that out in my notes. Right. Right, so let's just make a summary of everything we've proved so far. Right, so suppose C is contained in Fq to the n is a cyclic linear code. How much we can all remember. Right? Then the place to work with the cyclic code is not in Fq to the n, but to work in this ring R, which is the set of all polynomials over Fq modulo x to the n minus 1. So this polynomial multiplication where it captures the cyclic structure that this code has, right? So we call this method pi. Right? Instead of working with the code, we work with pi of c. And it turns out that pi of c is not just any subset of R. It is, in the language of abstract algebra, it's a ring, right? It has a generating polynomial. It turns out that there exists a unique monic g of x of least degree such that pi of c is equal to the set of all multiples of g of x modulo x to the n minus 1. That's the way you read that. Right? Set of all multiples of g of x modulo x to the n minus 1. Right? So that's the structure of pi of c. And last time I proved that the dual of this code is also cyclic. Did I prove that? You guys remember that? That C perp is also cyclic, right? this here is actually very, not hard at all, right? Because we know what the generating matrix for this code C looks like. So I'm just reminding you of stuff over here. So if my g of x is equal to g naught plus g1x plus gt x to the t, right? Then we saw last time that t equals n minus the dimension of the code, right? And my generating matrix for the code is given by g naught, g1, g, so I'm going to write this here as n minus k. Right? And then we have, let's see, the n minus k plus 1 entries over here, right? Accounting for that, and then n minus that, which would be k minus 1, zeros over there. Yeah? And then to get the generating matrix, I cyclically shift this here until this just about, well, is at the very end, n minus k. Here we have g naught, g1. Right? If I shifted any more, then this would spill over. Right? So that would be my generating matrix. So my generating matrix consists of cyclic shifts of this vector here. Right? A vector in the dual code is orthogonal to every code word in C. In particular, a vector in the dual code is orthogonal to every cyclic shift of this vector. Right? But that means that also, from one of your homework problems, that this vector here is orthogonal to every cyclic shift. It also means that every cyclic shift of these vectors, of this vector over here, is orthogonal to every cyclic shift of a vector in C perp. Did that make sense? Right? So a vector in C perp, a vector, let me say V, in C perp is orthogonal to every cyclic shift of this vector. Therefore, every cyclic shift of this vector is orthogonal to every cyclic shift of this vector, which means that every cyclic shift of this vector belongs to C perp, which means that C perp is cyclic. Right? So that's the proof that C perp is cyclic. Right? And of course, when you see that, immediately you want to know, well, what's the generating polynomial? Because you know that every cyclic code has a generating polynomial g of x, the way I just outlined over here. So what I spoke about last week was how to find the generating polynomial. Right? So generating of C perp. Right? And the method I gave you to do that, to find it, is as follows. So let h of x equal to x to the n minus 1 divided by g of x. Remember, g of x is a divisor of x to the n minus 1. Right? So we proved that g of x divides x to the n minus 1. So I can definitely divide out and get a polynomial. Right? So just make sure I get the right thing. Let h sub So let h sub naught be the leading coefficient of this polynomial. Let leading coefficient of h of x. And put don't put anything. Right. Then the result goes as follows. Then 1 divided by h naught times h perp. So remember, h perp is the polynomial obtained from h by reversing the order of the coefficients. Right? Then this polynomial here is the generating polynomial. Of C And the proof goes like this here. I would normally, actually at this point, for the sake of time, I would probably just skip the proof, but I like this proof so much that I want to write it down.
Sorry, just to clarify, so H is gonna be monad, right?
Yeah, so that's why I am dividing out by H now.
Is but H naught is the leading coefficient, so
Yeah,
would it
it's
be
the leading
one?
coefficient of H. Right? Yeah, this scaling factor is just to make this here monic.
Sorry, you're,
Or you think it should be the constant coefficient?
yeah.
Yeah. Sorry about that. You're right about that.
Okay,
Yeah, the constant coefficient. Yeah, because the order gets reversed.
yeah,
The constant coefficient becomes the leading coefficient in H. The constant coefficient of H becomes the leading coefficient of H per. Right? So, yeah, so I want to prove that this is a generating polynomial for C per. So my proof is going to have some arm waving, but I'll have my favorite part in it. Right? So, I'm not going to prove everything. You should be able to fill in the gaps. I might even fill in the gaps with my voice. Right, so I really like this proof. Something very interesting happens, and you'll see why. Should take a picture of this here. So that is the proof for most of it. So I'm going to write h of x as follows. So write h of x equal as follows. I had a good pen to move it over. There it is. I'm going to write g of x equals g naught plus g1x. Of course, the degree of g of x is n minus t, right? But I'm going to write this here with the full set of coefficients from a length n vector. So it's going to go all the way up to g n minus 1 x to the n minus 1. Did you all follow what I just did? The zeros at the end. Remember, as a vector, my matrix, my polynomial looks like this here. T is the degree, whatever it is, or it's n minus the dimension. And then there's a bunch of zeros. So I'm just going all the way up to that point. Right? So I'm going to write g of x as that. Right? So let me just emphasize that. And h of x I wrote this wrong in my notes, but that's fine. H of x equals h naught plus h1x. h1x plus hn minus 1 x to the n minus 1. Right? What's the degree of h, by the way? Someone? The product of g and h is x to the n minus 1, right? G times h x to the n minus 1. G itself has degree n minus k, so that means h will have to have degree k, right? So hk, right? I'm gonna write n minus k. Okay. So we have that. And we know that h of x times g of x is equal to x to the n minus 1. Right, we know that. Let's see. So this is my favorite part of the proof. It's very simple, right? So I'm going to rewrite this here as h naught. Maybe I'll rewrite my h first, g first. G of x times h of x. I'll rewrite this here as g naught plus g1x plus g, 20 more terms for sanity. No? Gn minus 1 x to the n minus 1 times h naught plus h1x plus h n minus 1 x to the n minus 1 equals x to the n minus 1. So I'm going to rewrite it like that. Right? And now that's an equation or an identity of polynomials, right? Everything over here is happening, this equation over here is happening inside this ring here in the set of all polynomials, set of all polynomials with coefficients in FQ. And now I'm going to go modulo x to the n minus 1. Right? In other words, I'm going to go to this ring over here. Right? So in R, that is modulo x to the n minus 1. This becomes g naught plus g1x plus gn minus 1 x to the n minus 1 times h naught plus h1x plus hn minus 1 x to the n minus 1 equals 0. Right, so that's what this becomes. Right? So I'm going to multiply out the left hand side. Right, I'm going to multiply out the left hand side. Right, by distributing everything. Right? So the way I'm going to do this is as follows. First, I'm going to find the constant term. What is the constant term when I multiply out the left hand side? Forget about what the right hand side is. Focus on the left hand side. I'm just multiplying two multiple polynomials out. What is the constant term when I multiply on the left hand side? What's the constant term? So g naught h naught would be part of the constant term. Yeah, so the reason I like this proof so much is that that's what I thought the first time I read it. It's not g naught times h naught. Not just a g naught times h naught. It's more than that. So here is your hint. When you're working in this ring, x to the n is equal to 1. X to the n power is equal to 1. Right? You agree in that way? So if I multiply this by that, g1x times hn minus 1x to the n minus 1. This is the same thing as g1 hn minus 1 x to the n power, which is g1 hn minus 1 times 1. Does that make sense? Yeah? So it's g naught times h naught, yeah, that's part of it, plus g1 times hn minus 1. Right, so that means there's more. What more is there? So I multiply these two. Now what's next?
G2
Plus g2 n minus 2. what's the last term?
G n minus 1 times h1.
Right? So that would be my constant term, right? And I really should have left more space for more terms. But let me just erase all. Right, everything over here is reduced, so I can take this out. Right, so actually I should put another term below. So that's the constant term. Now I want to know what is the coefficient of x. So of course it's tempting to write what?
G0
Yeah, g0
times h1.
times h1. Keep going.
G1 times h0.
So g plus g1 times h0. So this is what most people would say at the outset, but of course we have some more information now. Plus g2 times
So we're looking for the
coefficients of
that
x.
give us x to the n plus 1.
Say that again? Yeah, yes.
G2
Because we
times
pass on the whole score x
dx squared
stuff 0.
hn
hn minus 1.
Yeah, great.
Right, just for fun, a couple more terms.
1. G3 hn minus 2.
Yeah. And then the last term will be
G n minus 1 times h2.
h what?
h2.
h2. You all agree with that? The subscripts add up to n plus 1 from this point onwards. Right? Plus. So that's actually half the reason why I like this so much, is a little bit more. Right? The last term would be x to the n minus 1. Right? Because from every higher power can be reduced, right? So what's the coefficient of x to the n minus 1? So I'll give you the first one. G0 times h n minus 1. Give me the rest. There is a pattern that if you notice it, you'll be able to give it to me very quickly. What is it?
Well, we did like basically a cyclic shift on all the H ones.
Yeah, you see the HIs, first of all, the order got reversed. See Hn minus 1, Hn minus 2 right on to H1, and then H0, right? And from this point onwards, the H's are being cyclically shifted, right? So, if I have the starting point for this here, I can easily write down the rest, the other terms. So we have H1, remember the order is reversed. Right? So Hn minus 1, then will be Hn minus 2. Right? At the very end, we're going to have Gn minus 1. Right? And what's this here going to be?
h0.
H0. Hn minus 1 is the highest leading coefficient. Right? So H0. Yeah, it's a bad choice of, I don't know, maybe it's not bad. That's fine, that's H0. You see that? Right? And that whole thing is equal to 0. So that means that we have the following. So that's the other thing I like, is that in each subsequent term, the only difference between this and that is that the H's are shifted. Right? So matching the coefficients on both sides, right? We see that, right, so matching the coefficients. We see that vector G0, G1. Matching the what I really that's kind of silly. What I should say is that right, we see that all the coefficients that all the coefficients are 0. Right? This implies that the vector G0, G1, right up to Gn minus 1 is orthogonal to every cyclic shift of the vector Hn minus 1, Hn minus 2 down to H naught. Does that make sense? It's orthogonal to every cyclic shift of that. Right? So now at this point I'm going to start waving my arms, and I'm not going to prove everything, right? So this implies, right, and this here is a jump, right? Big implication that C perp equals the span of all cyclic shifts of Hn minus 1, Hn minus 2 down to H naught. Right? The H is in reverse order. Right? The proof is not hard. It's just a dimension argument, right? Because the set of all cyclic shifts of these vectors is contained in C perp. Follow? And this polynomial here is a divisor of x to n minus 1. So a very careful dimension argument to prove that. Right? And this implies that, again, right, smaller jump. That this polynomial here generates so if you don't buy my jump, just try and prove this by yourself. It's been proven in many textbooks, so you can believe me. Right? It's true. So now we can actually write down a generating matrix for the dual code as well. Right? So last time let's see. Last week in the recording of that video, I did go over an example, and what I want to do is go over another one. So I'm going to give you a cyclic code. So there's only one topic after this, because we don't really have much time. And the topic is decoding cyclic code. So there's a nice method of decoding an error if the error is trapped within a certain path. It's cyclically shifted first the beginning, and then use very simple methods to decode, right, certain errors. But yeah, for now, here's this example. Suppose that C is a cyclic code. Let me show this correct. C is the cyclic code generated by the cyclic code. length 6. Over F3. Generating polynomial, right, generated by x squared minus x plus 1. So the first thing to note is that that polynomial is a legitimate generating polynomial, right? And how do you check that? You need to make sure that this here is a divisor of x to the 6th minus 1. Remember that every generating polynomial of a cyclic code of length n is a divisor of x to the n minus 1. So if you look at x to the 6th minus 1, this is something that's very easy to factor, right? This is the same thing as x cubed squared minus 1, which is x cubed minus 1 times x cubed plus 1. Sum and difference of two cubes, right? And then they have formulae for factoring those. The first one is x minus 1 times x squared plus x plus 1, and the second is x plus 1 times x squared minus x plus 1, right? So these are standard formulas that I'm just using, and you can see that x squared minus x plus 1 is this formula over there. Is that factor over there, right? So that is a legitimate generating polynomial. The dimension of C is equal to what? It's going to be n minus the degree of G. So my G of x is given by this here. So it'll be 6 minus 2 equals 4. My generating polynomial, sorry, not generating polynomial, my generating matrix is going to have 4 rows in it, right? So they're going to be shifts of this particular vector. My vector over here is 1, negative 1, 1. The length is 6. Right? So that's my generating matrix for my code. Now for the dual code, to find the generating polynomial, I need to divide out first, compute h of x equals x to the 6th minus 1 over g of x. I have x to the 6th minus 1 factored here completely. I'm dividing out by this term over here, so this is the same thing as x minus 1, x squared plus x plus 1 times x plus 1. Right, and you can multiply this out your favorite way, but we got this from factoring x cubed minus 1. So we have x cubed minus 1 times x plus 1, and you can just multiply that out. Right, your constant term is negative 1. The coefficient of x is minus 1. There's no x squared terms. There's an x cubed term that would be x cubed, x to the 4th. Right, and I think that's it, right? You could have got that by just spoiling, right? So that's my polynomial h of x, and now I need to find h per. So I rewrite the same polynomial, but with decreasing powers of x. Does it make sense? So this would be minus. So there are different ways of doing it. So minus x to the 4th minus x cubed plus x squared. What did I just do? No, that's wrong. Don't do what I just did. Right? Yeah, this can be potentially tricky, right? So the thing is this here. Yeah, I fell into a trap that I set for exams, right? So,
Yeah.
so this is minus 1 minus x plus 0x squared plus x cubed plus x to the 4th. So there's a 0 term over there, You all follow? Right? So you can do this however you like. You can rewrite the coefficients in reverse order. Right? So I'll do that. So if I rewrite the coefficients in reverse order, we have 1, 1, 0, negative 1, negative 1. And then increasing powers of x. So plus 1 times x, plus 0 times x squared, minus 1 times x cubed, minus 1 times x to the 4. So that would be h per. Do you all follow what I just did? I reverse the order in which the coefficients appear. Right? And then of course I want it to be monic, so I'll divide out by negative 1. So negative h per will be minus 1 minus x plus x cubed plus x to the 4. Yeah, notice that this gives you the original h back again. Right? That's coincidence. Right? So this would be the generating polynomial for C bar. Right? So this is the generating polynomial. Right? Which means that I can write a parity check matrix. My parity check matrix will be, I know that C perp is cyclic. I have a generating polynomial, right? My words have length 6. And you give me this polynomial in vector form. We have minus 1, and then there's an x squared term over here. So there's a 0, we have 0. X cubed will be 1, x to the 4th, the coefficient is 1. And then my length is 6. So we have 1, 2, 3, 4, 5, and then I need to add 1, 0 on. Are you guys following me? Right? And now I need to shift this 1 over. So 0, minus 1, 0, 1, 1. Right? So that would be my parity check matrix. Right? So it's parity check matrix. Right? What's the minimum distance of my code, by the way? 2. Yeah, because you can see that, well, this is minus that. Right? So we have a word of weight 2. The columns are linearly independent, so there's no word of weight 1. So the minimum distance of the original code is 2. So let me ask you this. What do you think the minimum distance of C perp is? The minimum distance of C perp. So remember that this is the parity check matrix for that. But since the dual of the dual is the original code, that means this is the parity check, a parity check matrix for C perp. Does that make sense? Right? So for me to try and figure out what is the minimum distance of C perp, I would look at this matrix over here. What do you think?
I think it's 4, yeah.
You think it's 4? So let's see. Certainly, every pair of columns is linearly independent, right? So the question is whether every selection of 3 columns is linearly independent. If I choose any 3 over here, it will be linearly independent, right? So the only option or choice, so if the only 3 that I would, the only selection of 3 that seems that I would have to think about would be those selection that includes these 2 columns, right? And maybe so these 2 columns.
Well, by the same logic you're pointing out is the zeros that form the triangle on the bottom left, so the first 4 are linear independent.
Yeah, you can apply to the ones on the top.